Our topic for today is section 10.4, polar coordinates and polar graphs. Probably saw this already in pre-calculus, and generally this section is really mostly reviewing of that pre-calculus. So what is the main idea? First, this will sound somewhat similar to section 10.2 and 10.3. There will be lots of sines and cosines, but this is completely different. So we are not moving on the curve and then tracking our position with respect to time. We are actually describing the plane in a completely different way. And generally, here is the main idea. If you are in San Diego, for example, downtown, then streets and avenues go like this. So that's why if I explain my position here, I'll say, okay, I'm on the intersection of First Avenue and Third Street. And that's how rectangular coordinates work. But what if you are in Paris, for example, that has many of those, people say Lexington, Kentucky, where streets go like this. Or you are watching a concert at an arena, so there are those sections, and then in each section there are rows here. So then you would describe your position not using X and Y. You would express your position actually saying which sector are you in, and also when you know the sector, let's say I got a seat in this sector, and then I find a row, and then that's where I'll sit. So generally when you have circular objects, then geography requires a different description of points, and that's exactly, those are polar coordinates. So what do you do here? I'll do coordinate system just out of habit, although what we really need here is just this line. It's called polar axis. So polar axis. And when I want to represent point, so let's say I have a point M, then I report two things. One thing is the angle theta that OM connector with the center makes with respect to polar axis. And also I will report the distance. So that theta is actually which sector are you in, and R is which row are you in. And that's it. Basically what happens, this is equally good description, so if you give me theta, I will circle around and find on which array my position is, and then I'll go a certain distance, and this really tracks down all the points. And that's it. And you will see how nice it is for some type of circular objects. But the main thing to learn here is connection between these polar coordinates. So polar coordinates are R and theta. I like to put angle. This is not standard. But if you write two numbers, you don't know which coordinates are you talking about unless someone says it. So that's why I like to put angle theta to remind you that that's what it is. And here is X and Y rectangular. And then it's fairly easy if you want to see how rectangulars work. Here they are. This is Y. This is X. Simple triangle geometry tells you that X over R is cosine theta, and Y over R is sine theta. So if you solve for X and Y, you have the following formula. If I have R and theta, then X equals R cosine theta, Y equals R sine theta. So to go from polar to rectangular, that's very easy. The backwards process is slightly more complicated. Why? Because those equations are not so easy to solve for theta. What we normally do is the following. We divide those two. So we get what? Y over X is tan theta. And then you recover theta from that information, but that's a little tricky. I'll explain that in a moment. Before I get into that discussion too much, R is fairly easy because R is just Pythagorean theorem. So square root of x squared plus y squared equals to R. So that's easy. But this one is not. Why? Because when I get tan theta, then there are two angles that have the same tan. If you are on a circle, this angle and this angle have the same tan. The same way this angle and this angle. So they are across from each other. So when I get y over x, there are two possible thetas for me. But then it's not a big deal. You just see which quadrant you are in, and then, so generally I'll say the following: theta equals arctan y over x plus k pi, where k is 0 or 1. K is 0 or 1. You do arctan, and then if that angle is in agreement with your position that you just see where your xy is, then don't add anything. But if you see that theta that's suggested and your position disagree, add 1 pi. So sometimes we add pi, sometimes we take it as it is, as you will see from it. That's it. That's almost the whole section about that transfer of coordinates. And then more interesting part is how do we draw polar graphs just as polars, forgetting rectangular coordinates for a moment. So here's an example. Example, convert 5/2 4/3 rectangular to polar coordinates. We're just practicing what we just discussed. What will happen there? For R, I don't even need to think, so R is just square root. Let's do Pythagorean theorem. 25 over 4 plus 16 over 9. And how much is that? If I cross multiply, 9 times 25 is 225 plus 64 over 36. This is 289 squared root of 17 over 6. Here it is. R is always positive. For drawing, we sometimes allow negative r's, but I'd rather not even think of that when I do calculations. All right, so r is 17 over 6. What about theta? Tan theta equals y over x, which is 4/3 over 5/2. If I multiply by reciprocal, I'll get 8 over 15. So, let's say theta is, I go to calculator, arctan 8 over 15, and I don't know if I should add pi. So here it is, arctan always reports for positives here, for negatives here. So it's only first or fourth quadrant. If my point is in the first or fourth quadrant, that's it. If it's not, then I'll add pi. But my point is obviously in the first quadrant, so that's good. It's this, and then I don't know if I have something which is approximately 0.39. So here it is. So it was fairly. Here is an very interesting question. This is very trivial, just plug in the numbers. How do you convert a curve from rectangular to polars? So and that shows you the advantages. Why is this really worth learning? So number 34. Curve is given implicitly, and it's given like this: x squared plus y squared minus 9 times x squared minus y squared equals 0. All right, the curve is given implicitly, and I have no idea what to do with it. Why? Because it's implicit. What I can see is, since when you replace x with negative x, y with negative y, nothing changes, that curve is symmetric. However, it looks in one quadrant looks the same in all the others. For example, that's conclusion. A calculator will not draw this. So, if I solve it for y, solve a quadratic equation, that might give me some chance, but again, it's very unpleasant. But look how much nicer it will be if we go into polars. So x squared plus y squared, we know that that's r squared squared. Minus 9 times, this is r squared cosine squared theta, minus r squared sine squared theta, equals 0. Okay, so what is that telling me? I have r to the fourth minus 9r squared. What's left in parentheses? Cosine squared minus sine squared. There's a formula from trigonometry. Again, we pull out the 3. Cosine 2 theta equals cosine squared theta minus sine squared theta. So this I can write it much more compact. That's cosine 2 theta equals to 0. I can factor out r squared, and I'll get r squared minus 9 cosine 2 theta equals to 0. So what is that telling me? Either r equals 0 or r squared equals 9 cosine 2 theta. R equals 0 is just to contain the origin. So if I get origin here, then there's no reason to do that. So here it is. My equation looks actually much better. And this is the first polar curve that we will draw. So how do we draw this? Generally, here it is. When we draw, generally I imagine all those sectors here, and I plug in some values. So here it is. I plug in theta, and then I'll get r. A little comment is when I see a function that has exclusively cosine. Since cosine is even function, when I replace theta with negative 2 theta, my curve looks the same. So that tells me it looks the same up and down. So if you have cosine, so r is a function of just cosine theta, then we have this symmetry. Symmetric with respect to x-axis. If it's exclusively of sine theta, then it's symmetric like this with respect to y-axis. There's one more symmetry, but these two are a good start. So this one will look the same up and down. So what do we do? So I will go from 0 to pi, maybe not even to pi. Let's see what happens. I'll go here and plug in 0. And then I'll plug pi over 8. And you will see y is so fine, and then pi over 4. Then I'll plug in pi over 2. This is not trivial. As I said, calculator can do that, but if you do it by hand, I strategically chose those values. Why? Because r squared is 9 cosine theta. So then r squared is 9 here. So r is 3. So that says when theta is 0, so in this row, so theta is 0, theta is pi over 4 is here. Theta is pi over 2 is here. Theta is 3 pi over 4 is here. And pi will be there. So theta is pi will be here. Okay. So what happens? When theta is 0, r squared is 9, r is 3, so I will have something 3 steps away. 1, 2, 3 on that ray. When theta is pi over 8, I didn't even draw pi over 8. I'll get what? R squared is 9 times cosine pi over 4. So that will be 9 root 2 over 2. I don't need precise calculation here. So this is like a what? 9 root 2, maybe this is approximately 6. Because this is 1.4, 13.6, maybe 6.7 or something like that. And then R is square root of 6.7, so that's approximately 2.5. So what will happen on that ray under all will shorten. But then, let's say approximately, so this is just for drawing purposes, approximately, let's say 2.5, maybe 2.6 is better. Maybe 6.5, yeah. As I said, if you put it in the calculator, you will get exactly what it is. At pi over 4, something interesting happens. Why? Because r squared is 9 cosine pi over 2, but cosine pi over 2 is 0. So generally what will happen, our r is 0. So generally we come back here. So generally our cosine was decreasing. On those rays I was going shorter and shorter, and again I came back. And I came there at the angle pi over 4. Then between pi over 4 and pi over 2, there's nothing. Nothing. Why? Because between those two, between pi over 4 and pi over 2, so like theta is between pi over 4 and pi over 2. 2 theta is between pi over 2 and pi, and cosine is negative, so I get negative number on the right, positive on the left. This is impossible and nothing there. The same thing happens between pi over 2 and 3 pi over 4, because cosine 2 theta is still negative, so I have nothing here. And then finally, between, so at 3 pi over 4 I got 0 again. And then what happens here at pi, basically when I double it, so when theta is pi, cosine 2 theta is cosine 2 pi, which is 1, so I get r squared to be 9, so I get my 3 back. So at pi, generally at pi here, I get my 3 back. Actually, my curve was recovering. And then if you remember, we said because it's purely cosine, look the same up and down, so I don't have to draw more. So connected is the same up and down. And here is a very interesting curve. This curve is called a Leibniz-Curve. Like a loop. So Leibniz-Curve. So here is how they're drawing. So generally, you know, there's nothing fancy here, like plugging in points. In rectangular coordinates here, we also plug in points, but we kind of change angles. So basically, when you do polar drawing, you kind of always make a good net. Of course, you have to choose it, maybe sometimes pi over 4, sometimes pi over 3. So, and then for each of them, you calculate r and place a point, and then you connect points, and that's it. Just your trigonometry has to have some basic qualities, and that's what we have. All right, here is one problem that's actually trivial, but if you are careless, you can run into troubles. What is it? We are not going to go from rectangular to polar, we go the other way around. So you take number 42, convert r equals 2 over sine theta into rectangular coordinates. So, what could make this problem? Please be careful with my next few sentences. People are often tempted. What are our formulas? R equals square root of x squared plus y squared, and tan theta is y over x, and maybe plus that k pi. But here it is. So people are tempted to, I studied, I memorized the formula. So I say, oh yes, I remember that formula from last night. You plug in that square root, and your troubles are there. So remember the order of addressing the quantities. Forget r for a moment. Address theta first, and keep r. So address theta first. So get rid of theta. So how do I addressed not this way. There is formula y equals r sine theta. So from that formula, I know that the y over r is sine theta. And that's what I want to use. So what will happen? X and y will appear. R will still be there, and that's okay. I will deal with R the way you want it, but at the end of the story. So I say R equals 2 over y over R. And then little polishing, so R equals 2 times R over y. Here it is. Sine theta is gone. I'll deal with R now and replace everything. So sine theta, deal with cosine and sine theta first, using those basic formulas, not those complicated ones. And then something very strange happens here. I multiply by y both sides, and I get the following. Ry equals 2r. Then I cancel by r, which is okay. So if r is different from 0, I cancel and I get y equals to 2. And then what? Generally, r cannot be 0. Why? Because if you want r to be 0, this quotient can never be 0. So there are no restrictions that I placed. Here I got y equals 2. Generally, what is that equation? It's just horizontal line. And of course, what the common sense telling us now? For this object, I would never use polars, so polars are not appropriate here. So use them where they are appropriate, don't use them where they are not. Of course, this is a rectangular object and not a polar object. All right, and then now we will do one problem, calculus problem. So tangent line to a polar object. So what would that be? By the way, we'll learn how to draw one of the most famous polar curves called cardioid. So here's the story. Problem number 60. It says the following: find dy over dx and slopes of the tangent lines at given points. In your book, this graph is given. I'd like to discuss how to draw the graph. So r equals 2 times 1 minus sine theta. All right? So first up, I'd like to practice how to draw this, and then I'll place those points where they want to calculate tangent line, and that's what we'll do. So the question is, how do I draw this? So we said the following coordinate system, and then we make a table strategically. So what? My lowest value for theta will be negative pi over 2. This is periodical, of course. So I'll go with negative pi over 2, and I will finish at pi over 2. Why? Because I'll start here, wherever it is, calculate the values, here, 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 and I'll start here. Why? Because I see purely sine, so I see left and right graph looks the same. So when I get the right graph, I just copy it to the left. We said that if you have exclusively sine theta, you have symmetry with respect to y-axis. So I draw this right part, and then I'll do the left part. So what happens at negative pi over 2? I get, what? 2 times 1 minus sine of negative pi over 2. Sine of negative pi over 2 is negative 1. 1 minus negative 1 is 1 plus 1, so I get 4. And then let me go negative pi over 4. I'll go a little faster. 0 pi over 4. What happens at negative pi over 4? It will be 2 times 1 plus root 2 over 2 minus negative 1 plus root 2. So it will be a little shorter than what I have. So that will be what? 2 plus root 2, which is approximately 3.4. And then at 0, I'll just get, so this will be approximately 3.4. At 0, I'll get sine 0 is 0, so I'll get 2, obviously. pi over 4, I'll get 2 times the 1 minus root over 2, which is 2 minus root 2, which is approximately 0.6. And at pi over 2, I'll get 2 times the 1 minus 1, so I'll get 0. So generally what happened is that my r got shorter and shorter. I started with 4, intermediate value was 2, and here, so here are my rays. So here is this ray, here is this ray, negative pi over 4 got fairly long. This, and then at pi over 4 it became quite short, and then it became 0. So if I connect all those points, here's what I'll get. This turns, gets short, and comes back. And then what happens on the left? We just copy to the left, and we get a heart-shaped curve. And that's why it's called cardioid. Vertical cardioid. So it looks like heart. That's what the name says. All right, so that's our cardioid. And they asked us to calculate slope at a few points. One of them is 2, 0. So here's the point 2, 0. That's A. And they wanted point B, which is 3. So here's point B, which is 3. And angle is 7 pi over 6. And then at point C, 4 and 3 pi. Actually, it's particularly interesting for me to find what happens at point C, because very often people draw a heart with a cusp here. So my question is it really like a heart with a cusp, or it has, it's differentiable? That means if there is a tangent line. So, wait a minute, we didn't develop formulas for the slope of the tangent line, but generally we don't need that because we'll just use parametric equation. Why? And your book wrote a huge formula. I don't suggest that you memorize that because it's not necessary. So what would that be? We know that x equals r cosine theta, but r is a function of theta. So it looks like this. Y is our sine theta, so that would be r of theta sine theta. So generally I can think of this. This is not the main idea, but I can think of this, that actually my curve is actually parametric curve of theta. So x equals this times cosine, y is this times sine. So generally I can use what we learned in the previous section. So we get what? The dy over dx equals, what would that be? D over d theta, r of theta sine theta. And on the bottom, d of d theta, r of theta, cosine theta. And then I just product rule, and that's the formula from your book. So what would that be? dr over d theta sine theta plus r times cosine theta. At the bottom, dr over d theta cosine theta plus minus r sine theta. Here it is. By the way, what is dr over d theta? dr over d theta is what? Derivative of this. So that will be negative 2 cosine theta. So generally it will be what? Negative 2 cosine theta sine theta plus 2 times 1 minus sine theta, which is r, times cosine theta, or dr over d theta, so negative 2 cosine theta squared, actually, because it's what? Dr over d theta times cosine theta. So already have cosine, so then negative 2 cosine squared minus r sine theta, so 2 times 1 minus sine theta course, this is all conditional calculation if I'm not getting 0 in the denominator. So when I finish calculation, I might exclude some points. So what would that give us? Minus 2 sine theta cosine theta plus 2 cosine theta and minus 2 sine theta cosine theta. I don't know, maybe we are on the screen here. And here I get minus 2 cosine squared theta minus 2 sine theta and plus 2 sine squared theta. So finally, this expression is, I can combine these two and get what? Minus 4 sine theta cosine theta plus 2 cosine theta. On the bottom, I'll get what? Here I like everything to be in terms of cosine, so I'll trade minus 2 times 1 minus sine squared theta. So I'll get minus 2 minus 2 sine theta and plus 4 sine squared theta. Because those plus 2 and plus 2 give me 4. Let me check my calculation. So I factor minus 2 cosine theta, that's fine. Minus, I left it the way it was. That doesn't matter. All right, and then what we do, we just do the calculation. So at A, what would the slope be? When, how much is theta? Theta is 0. So sine theta is 0, cosine, so we get 2 over sine is 0, it's minus 2, so we get negative 1. So basically that's the slope. Makes sense. What about at B? So what we do there, that 7 pi over 6, they are both negative. So maybe I should really factor out here 2 cosine theta times 1 minus 2 sine theta. Yes. Well, it doesn't matter. Might be nicer. So cosine of 7 pi over 6 is minus root 3 over 2, but minus root 3 because it's double. So it's minus root 3 for cosine, and then sine is negative 1/2. So negative 2 times 1 and 1 is 2. So negative 3 times 2. On the bottom we will get 2 minus 1 plus 1, because sine theta is 1/2. So this cancels, 2 cancel, and looks like minus root 3 for me. Oh, on B, I know on B, I didn't do calculation correctly, sorry. 2 minus 2 sine, did I mess it up there? Cosine squared, minus 2 sine squared. Oh, here it was, yes, minus 2 sine. Minus 2. Oh, it's minus 2, sorry, I got it down. Minus 2, it's here. So what would that be? So it would be minus 2, and then plus 1, because it's negative, and plus 1, so we get 0 here. So what happens? Actually, I couldn't apply the formula, but if you remember our discussion, if y prime of theta is different from 0 and x prime of theta equals to 0, we have vertical tangent line. Slope is infinite. So generally that point B is closer here, and that's exactly the point B. And then what happens at the point C? Let's do the calculation. So what happens at the point C? At point C, angle is theta is 3 pi over 2. So my M will be what? cosine is a 0, because cosine of 3 pi over 2, so we get 0 on top. What do we get on the bottom? I hope we don't get 0 again. Minus 2. Sine theta is negative 1, so it will be plus 2. And plus 4, because sine is negative 1, so we get 0. So what will that tell you? Function is differentiable, and the tangent line is horizontal. So generally, proper drawing for cardio, it should be much milder here without that cusp that people normally draw for these graphs. Okay, so that was the discussion about polar coordinates.